Okay. So last Friday, we started to introduce the concept of vector space. So a vector space over R is just a set V of elements. And these elements will be called vectors, together with two algebraic operations. Right? One is called vector addition, the other is called scalar multiplication. For vector addition, the plus is that for every pair of vectors in the set V, we have sum of U and V, all right? And this sum is in V. And also we define an operation for a real number here and a vector in capital V, such that the value is a scaled vector U by alpha. So it's alpha times U. So you scale the vector V by alpha. Okay, so we have V, we have vector addition, we have scalar multiplication. All right, and the following axioms are fulfilled. Okay, so there are 7 axioms. I will state one by one. The first one is called associativity of vector addition. Okay. All right, so that says that U plus V. So you take the sum of U and the V, and then take the sum with the W again. All right. This is one way to do 2 vector additions. And this is equal to, you take the sum of V and the W first, and also then take the sum with U. And the result will be the same for all U, V, and W in V. Okay. So this is the so-called associativity of vector addition. Now the second axiom is called a commutativity of vector addition. All right, so U plus V should be equal to V plus U. Okay. All right, so this is the second axiom. Okay. So no matter which order you have, that the result will be the same. Okay. So it's called a commutativity of vector addition. The third one is the existence of a zero vector all right. So there is an element denoted as 0 in V, such that U plus 0 is equal to U for all U in V. Okay? So when you add a 0 to any vector U, you do not change anything. All right? So the sum will be equal to U again. Right? This is the first one. Now the fourth one is called the existence of additive inverse. Okay? Now for each U in V, there exists an element denoted as U tilde in V, such that U tilde plus U is equal to the zero element, right, in this third axiom. Okay. The fifth one is called a distributive law. Distributive law. Okay, so actually we have two distributive laws here. Alpha U plus V is equal to alpha U plus alpha V, and alpha plus beta U equal to alpha U plus beta U for all alpha beta in R and UV in V. Okay. So you can dispute alpha, the scalar, to the sum. Okay, alpha to U, alpha to V here. Okay, or you can dispute U to the sum here for two scalars, alpha U, beta U here. The sixth axiom is called associativity of scalar multiplication. Okay, right? So when you can do the multiplication of two scalars and then do scalar multiplication with U. This is one way. The other way is that you can do scalar multiplication with U to get a new vector and then do the scalar multiplication with alpha again. Okay. Okay. And the last one is called the unitary property. Right? The scalar 1, very special. The scalar 1, do the scalar multiplication with U, any vector, well, we'll give you U again. Okay. All right. All right, so we have 7 axioms. All right, as I made a remark last Friday, you know, the purpose to define the concept of a vector space is to try to extend our experience on vectors in Euclidean vector space. to more general settings. Okay, because for example, we learned about linear combinations, or learned about linear transformations. Right, and a lot of way to solve, for example, system linear equations. And it turns out that in the other branches of mathematics or engineering or economics or finance, that there are situations that we can turn the problems into, for example, system linear equations. Okay, and then we can apply what we learned up to now to solve the system linear equations, and then go back to solve our original problems in engineering or economy or in finance. So that so we have to develop the ability to do so. And one of the key concepts is the concept of vector space. All right. Okay. And you can find that you will have to verify some conditions for a system or a set to be called a vector space, and then we can apply our techniques there. Okay? Any questions about the statement of the definition of a vector space? Okay, now, before we take several examples of vector spaces, I would like to deduce some consequences of the 7 axioms here, as like we did in Euclidean geometry in junior and high schools. Okay, the first one. In axiom 3, it states that there exists a zero vector, okay, with this property. And this zero vector serves to define the existence of additive inverse, right? So that for every vector you have a vector you tilde such that the sum is equal to this zero vector. So a question is that is zero vector unique? So, and the answer is yes. Okay, so the answer is yes. All right, so the existence has been put in axiom 3. So we only needed to prove the uniqueness of zero vector. So let 0 and 0 prime be 2 zero vectors in B. Okay, then 0 prime. 0 prime is equal to 0 prime plus 0, since 0 is a zero vector. By axiom 3. Right? So 0 prime is a vector, right? So 0 prime plus 0 is 0 prime. Okay, so 0 prime is 0 prime plus 0. And now 0 plus 0 prime plus 0 is equal to 0 plus 0 prime by the commutativity of vector addition. This is Axiom 2, right? This is Axiom 2. All right, so we exchange the order of vector addition. And now this is 0, since 0 prime is a 0 vector. Okay? All right, so that they are the same. So 0 prime is equal to 0. All right, so 0 vector is unique. Okay. No other vector can be a 0 vector. Okay. Now, alpha is a scalar, arbitrary scalar. All right, so we do the scalar multiplication of scalar alpha and the 0 vector. And the result should be 0 vector for any scalar alpha. All right. All right, so this. Now, so we look at since alpha is 0 is equal to alpha 0 plus 0, okay? Because 0 is a 0 vector. So 0 plus 0 is 0, okay? Being the 0 vector. Okay, and now by the distributive law, we have right. So we distribute alpha into there. Okay. So now we have this one. Now, so you put the inverse of alpha 0. Right? By Axiom 4. Right, so we put an inverse of alpha 0 together. Alpha 0 together is a vector. Okay. Okay, by Axiom 1, by the associativity of vector addition, so we can do that. Okay? And this implies this is 0. Okay? This is 0. Why? By 4, right? This is 0. Because an inverse of alpha is 0. When you add together, you get 0. And this is 0. And plus alpha is 0. Okay, again by axiom 4. And this is alpha 0 plus 0 by axiom by the commutativity 2. And this is alpha 0. Okay. Right? So you can exchange the order. And then you get the, because 0 is 0 vector, so this is by axiom 3. Okay? And this is the end. Okay, so if when you do the scalar multiplication of arbitrary scalar alpha and the 0 vector, you get the 0 vector. All right, in the proof, what we can have is that we have only 7 axioms here, and the previous theorem we can have. All right, so if we know a scalar multiplication alpha u is equal to the 0 vector, then either alpha equal to 0 or u equal to 0. Okay. Okay, if alpha is 0, so we have done. Right? So if alpha is 0, we have done. So now we, if alpha not equal to 0, then we have alpha okay. So now we multiply, we do the scalar multiplication of alpha inverse, because alpha is not 0, so alpha inverse exists. You know, any scalar in here, scalar is real numbers. Any non-zero real number has a reciprocal, right? So, all right, and this is a scalar. We do the scalar multiplication with the scalar and the 0. And we just prove here, this is 0, right? Already, this is 0. Okay, so this is by theorem 2.4.1. Okay, we just proved. But the other way is we go this way. Okay. So why this is true? This is from the associativity of scalar multiplication. So this is axiom 6. Okay. All right, and this is 1u. Okay. But 1u is equal to u. Why? This is axiom 7, the unitary property. Okay, so this is the middle, right? We reach to the left-hand side, you get to u here. When we reach to the right-hand side, we get to 0. Okay, so u become to 0. End of proof. Okay. So if alpha is not equal to 0, we show that u is equal to 0 here. Any questions? So once again, I have to emphasize that what can we have is just the 7 axioms. And at this moment, we have theorem 2.4.8 and 2.4.1 here. Okay. So this is exactly Euclid did, right? More than 3,000 years ago. Euclid gave axioms, right? One of the famous axioms is that 2 points in the plane determine a line. Okay, that is an axiom. You can't prove it. Right? So there's a lot of axioms given by Euclid. And then he ended up deduce a lot of theorems, including like congruence theorems of triangles, right? You have ASA, you have SSS, you have SAS, you have ASA, a lot of triangular congruence theorems. You have a lot of theorems about the parallel lines, okay? And they all start from the axioms given by Euclid. Here we follow the same approach that we have 7 axioms given for a vector space, all right? And try to deduce some useful information about the vector space itself. For example, in this theorem, we know that the zero vector stated in axiom 3 is actually unique. No other zero vector, only this one. All right? And we also know some property that any scalar, do the scalar multiplication with zero vector, you get the zero vector again. Okay? And here, if you have a scalar multiplication that the result is zero vector, then either the scalar is 0 or the vector u itself is 0. No other possibilities. Which means that if alpha is non-zero scalar, and if u is a non-zero vector, then this scalar multiplication gives you a non-zero vector. You may think about that is nothing, right? This is obvious, but it's not very obvious. Okay. It's especially in certain situations. Okay. So that, but now we are happy to have this result. Okay. Now, similarly, in axiom 4, it states the existence of additive inverse. It says that for each u, you can find an element u tilde such that u tilde plus u is equal to the zero vector. Right? So the axiom 4 gives you the existence of the inverse. Now we will show this inverse is unique. Okay? So each element u has 1 and only 1. And the only one inverse. I have to say additive inverse. Okay. Proof here. So now we fix a vector u in the vector space. Now we let u, x, and y be additive inverse of U, i.e. we have x plus u equal to the 0 vector and y plus u equal to the 0 vector. Okay, we have that. Now we have to show x equal to u, y, right? Then we have x. All right, now x, we start with x. X is equal to x plus 0, right? Because of Axiom 3, right? And now 0 is y plus u. Okay, this is by substitution here. So we do the substitution. Okay. And now we change the order of this sum. So this is Axiom. The commutativity is Axiom 2. Now we use Axiom 1, the associativity of vector addition. So we associate, we take the sum of x and u first. And then now we apply here, this is 0 plus y. And y plus 0. So here is Axiom 2, the commutativity. And this is y. This is Axiom 3 for a 0. And then we have done. So we start from x, we end up with y. So they are equal. Okay? So we use the 7 axioms, and then we use what we have already, and end up with x equal to 1. Okay, so additive inverse. Okay, additive inverse is unique. All right. If the scalar is 0, then 0 scalar multiplied with arbitrary vector, the result is the 0 vector. Okay. All right, so we start with 0u. Now 0u plus 0 vector. So this is Axiom 3 for the 0 vector, all right? This is Axiom 3. 0u plus u plus u. Now we we use the axiom 4. Okay. Because a vector and the sum of inverse and the vector is equal to 0. So this is axiom 4. Right, by commutativity, this is axiom 2. Okay. And now 0u plus u. So this is axiom 1, the associativity here. And this is u plus 1u plus u. So what is that? It's axiom 7, the unitary property. Because u is equal to 1 scalar multiply with u. Now, by the distributive law, so what is that? This is axiom 6. And this is 1u. Because 0 plus 1, because we know the rule of real numbers. All right, 1u. All right, this is rule. And this is u plus u tilde. What is that? Again, this is axiom 7, right? All right, and this is u tilde plus u. So you change the order of summation. So that is axiom 2. And this is 0. This is axiom 4. And then you have done. So you start with 0 scalar multiply with u, and you end up with 0. Okay, so you get your theorem here. All right. Okay. And then the final elementary property is that now we know that additive inverse of u is unique. Okay, it's unique. And this unique additive inverse of an arbitrary vector u is actually equal to -1. -1 is a scalar, right? Multiply with u. Okay. So now it's easier for us to know what is the additive inverse of u. Actually, it's -1. The -1 is the scalar multiplication with u. All right. So the proof. All right. So we check. Right. So this one is a vector. We check with that. And we find that this is 1u. So this is axiom 7. Okay, it's 1u. And by associativity of scalar multiplication, so this is axiom 6. And we know in real numbers, -1 plus 1 is 0. So it's 0u. Okay? And 0u is equal to 0. By what? By what we would just, this is theorem 2.4.4. Okay, so this vector plus u give you the zero vector. All right? Now, so by the uniqueness of additive inverse, we just show that the theorem gives us that we have one and only one additive inverse for U. So by theorem, 2.4.3 must be equal to the U tilde. Okay? Because additive inverse is unique. Right? And this vector serves as the additive inverse of U already here. So that. Okay. Questions? Okay. So I list of the 6 theorems. The main point is that zero vectors in a vector space is unique. For any vector U, its additive inverse is unique too. And this unique additive inverse can be represented as a scalar multiplication of -1 and the U itself. It is a very convenient representation. Very, very convenient. You know all this about in the Euclidean vector space, right? In column vectors, you know all this. This is you all know. But when you deal with abstract vector space, you still need to check it again. Everything should be built from the 7 axioms. Okay, because you are talking about general vector spaces. Any questions before I illuminate several examples of vector spaces? Okay. Now I will okay, let me give a poll. If you have taken differential equation, I mean ordinary differential equation before, or if you are taking ordinary differential equation this semester, please. No. I think many of you were taken or just taking. I changed my question. If you did not take any ordinary differential equation course before, you and also, okay, how can I say it? It's a logical phrase. Okay. Okay, let me say that if you didn't take any ordinary differential equation course up to now, all right, up to now, please raise your hand. Oh, okay, thank you. Okay, so okay, I will refrain myself because I'm trying to take an example from ordinary differential equations. Suppose you want to solve a system of differential equations. Okay. Well, but because some of you didn't take any such course before, well, I will not do that. Okay. All right, so I try to do something will be familiar with you. Of course, you can give me a hint if you don't mind. That I take some examples from differential equations. Anyway. All right, so example. All right, so well, later, okay, maybe I take one. The set of all real polynomials okay, so P now is V, right? P is served as V, the set V. So P now is the set of all real polynomials. All right, so the degree can be 0 degree, 1 degree, 1 degree 2, etc. So arbitrary real polynomials. Now, okay, define two algebraic operations here. One is called vector addition. P goes to P in the following way. A pair, so we have summation I from 0 to n and AI xi. Right? So this is a polynomial, right? We say n plus 1 terms. The other okay, that is this one. Then how do you add the two polynomials together? Okay, well, you will find that which one has the highest degree, right? So that this you get the maximum of n and m and I from 0. Okay. Okay, and you have a I plus, so you select terms you put together and merge the coefficients. Xj here, xi. And with ai equal to 0 when I is greater than n, and bi and the pi is 0 when I is greater than m. Okay? All right, so you define, this is the definition, and you're all familiar with the operation of to add the two polynomials, right? I suppose, otherwise you can't be here. If you don't know the addition of two polynomials, you can't to be a student in NTHU, right? So that this is the definition, it's just a definition. And I check the ordinary addition of two polynomials. Second, the scalar multiplication. Right? So it's R goes to P. And here is alpha. Okay. So that the result of this scalar multiplication is that alpha AI So basically, you multiply each coefficient AI with alpha. So that is the meaning of scalar multiplication for polynomials, right? Right. So basically, this is the idea of scalar multiplication. Okay. So now we talk about polynomials and two common operations on polynomials. One is the addition of two polynomials. The second is the multiplication of polynomial by a scalar. I mean here, a scalar, it means a real number here, right? So, and the meaning here is that we multiply every coefficient in the polynomial by alpha. Okay, by alpha there. Now you have to check the 7 axioms. All right, and I will check them verbally, all right? Because I don't, I want to write it down one by one. Okay, first one. Association of vector addition. I think you already know this when you manipulate addition of polynomials, right? So if you have two polynomials, you can, okay, they are represented by here, H, G, H, they are polynomials. Then you can add the polynomial and then take the sum to add with H. It's the same as you take the sum of G of these two polynomials and then do the addition with fx. All right, so for the polynomial, addition of polynomials, you know the associativity law, and you know the commutativity because you can change the order of the reason is because that you can change the order of the addition of two real numbers. Okay. All right, so you have axiom number 2. What is axiom number 3? What is the zero polynomial? Zero polynomial is just a polynomial with zero coefficient. So you all know the zero polynomial. So zero polynomial is the zero vector. Because every polynomial adding with the sum with the 0 point will be the same, right? Will not change it. What is the inverse? Well, just -1, right? You know, if you have polynomial, then you change all the coefficient into its minus, its opposite. Then you get the inverse. Okay, so you have axiom 4. What is axiom 5? The axiom 5 is distributive law, right? And for distributive law, you know all this for polynomials and the real numbers. And axiom 6, the same, you know that. And 1 times axiom 7, 1 times a polynomial is equal to the polynomial itself. Right, so for this one, so let me say from high school, so I just say, from your study in high school, okay, you know all 7 axioms are fulfilled. That's P is a vector space. Right, so from now on, the set of all polynomials, since it's a vector space, so that we can use the technique or the concept we learned in this course up to now to apply to P, to the set of to the vector space of all polynomials. Okay, now let me get into an interesting example. So we let C, right, defined to be the set of all real valued continuous function or continuous functions on, sorry about that, I forgot to put the X there. Okay, so it's okay, and I assume you know the meaning of continuity of a function. Okay, so it's a set of all real valued continuous function. So now we define two algebraic operation. One is vector addition. Okay, so it's goes to the same. Okay, and the ft gt goes to ft plus gt. And second, scalar multiplication. Now, we have questions, actually. You take two continuous functions, right? Because the set says that every member is a continuous function on -1 and 1, this interval. And then you add them together. Of course, it's the addition of two real value functions, and I assume you all know that. Just add the two real numbers, real values together. But you need to verify that. Is the sum continuous? If f and g are continuous. So there is a question, right? You have to show that the sum of two continuous functions is continuous. You have to show that. But very fortunately, in calculus, it has been done already, right? I believe. I believe that because when I was a freshman, yeah, my professor did that for me, for us, for all the students in the classroom. Okay, so I believe you know that. So there is a theorem. So that must be a theorem, okay, in calculus. So to have this vector addition to be well defined, you have to verify that. So it's not for granted, you know. It takes some effort. So you have there is theorem saying that the sum of two real valued continuous function on -1 and 1 on an interval in R is continuous, right? So this has been proved. Okay, so there must be a theorem in your textbook, calculus textbook, that the sum of two real valued continuous functions on an interval, not necessarily this closed interval, right? Can be open interval, can be half open, half closed, or can be the whole real line. Anyway, any interval in R is continuous. And similarly, if you have a scalar and a continuous function, is this new function continuous? Well, you still need a theorem too. Okay, and fortunately, that theorem has been proved in your calculus textbook. Okay, so you can't take for granted that this mapping is always true, right? You have to prove that. The result is in here, because the codomain here is the same as this set. Okay, so you must have another theorem . All right, so again, the proof. Okay. All right. I'm sorry. Maybe I'll steal 5 minutes from your break time. All right, so the vector addition scale multiplication are well defined because you have two theorems in calculus. Okay? Not like in P here, because this is true, but because it manipulates polynomial quite often, right? So you know that this is a polynomial in P, of course. And also, this is also a polynomial. So there's no doubt for that. But for continuous function, for example, later on, what if I define a V is the set all real value twice differentiable function? I put more and more restrictive condition on that. Then, if two functions are differentiable, if their sum differentiable, you need to prove that, right? In your fundamental differential equation course, right? So you must have a theorem to support the result. Okay. So just like this one. So even to define algebraic operations, to make it the definition to be well defined, sometimes you need to take efforts on that. Okay. For example, in here you have two theorems in calculus. Okay. Okay, and now we can check, because I have no time. Actually, it's not necessary to do so, because from your calculus. Okay. All right. So you know, for example, functions. The addition of real value functions has associativity, right? And the addition of two real value functions are commutative. The order of addition is not potent. And the zero function is continuous function, of course. So zero function is in here. All right, so this vector space has a zero function because zero function is continuous. Okay, you can prove that zero function is just like any constant function is a continuous function. Okay, and the inverse, all right, just multiply with -1. Okay, so you have inverse, and distributive law, of course, you have, and associativity law for scalar multiplication, of course. And the one times a function is also itself. So Axiom 7 is also true. And so that for this set, all 7 axioms are fulfilled. And then it's a vector space over R again. Okay? So this function space, so it's a vector space of continuous functions. All right? It's a vector of continuous functions, and so later on we can apply our techniques to this vector space of functions. Okay, so I stop here, and continue several interesting examples of vector space on Friday.